Good day, sir, and to all of you. Welcome to the MathemaTeachTalk, proudly presented by the House of Samson. Today, we are excited to share our lesson on limit of transcendental function and continuity. We've prepared this discussion to help deepen our understanding and make learning more engaging for everyone. And here's the objectives. Objectives number 1. Transcendental functions. Recognize functions like exponentials, logarithmic, and trigonometric functions. 2. Limits. Understand and calculate limits, especially for transcendental functions. 3. Continuity. Know when functions are continuous at specific points. And lastly, number 4. Application. Apply limits and continuity to real-world problems. So without further ado, let's begin.
Transcendental function. In mathematics, a function not expressible as a finite combination of the algebraic operation of addition, subtraction, multiplication, division, raising to a power, and extracting a root. There are 3 types of transcendental function. There are exponential function, logarithmic function, and trigonometric function.
Exponential function. Y is equals to b raised to the power of x. Number 1. For all real numbers, c, the limit of b is raised to the power of x. As x approaches to c, x is equal to b raised to the power of the c. Number 2. If b is greater than 1, then the limit of b is raised to the power of x. As x approaches to positive infinite, x equals to positive infinite. The limit of b raised to the power of the x. As x approaches to negative infinite, x is equals to 0. Third column. If 0 is less than b and less than 1, then the limit of b raised to the power of x. As x approaches to positive infinity, x equals to 0, and the limit of b is raised to the power of the x. As x approaches to negative infinity, x equals to positive infinity.
Exponential function examples. Using the first theorem, let's have the first given. Limit of 4 raised to x as x approaches to 4, that is 4 raised to 4 equals 256. For the second given, let's use the second theorem. Limit of 2 raised to x as x approaches to infinity equals infinity. For the last given, we're going to use the third theorem. Limit of 1/2 raised to x as x approaches to infinity equals 0.
Logarithmic function. Y equals log base b of x. For all real numbers number c, the limit of log base b of x as x approaches c is log base b of c. If b greater than 1, the limit of log base b of x as x approaches infinity is infinity. The limit of log base b of x as x approaches 0 from the right is negative infinity. If b greater than 0 and less than 1, the limit of log base b of x as x approaches infinity is negative infinity. The limit of log base b of x as x approaches 0 from the right is infinity.
Here are the examples of the logarithmic function. In number 1, we have the limit of log to the base 2 of x as x approaches to 42. So, the limit of log to the base 2 of 42 is equal to 5.39. In number 2, we have the limit of log to the base 2 of x as x approaches to infinity is equal to infinity. In number 3, we have the limit of log to the base 1/2 of x as x approaches to infinity is equal to negative infinity.
Number 3. Trigonometric function. For all real numbers, the limit of sine of x as x approaches to c is equal sine of c. The limit of cosine of x as x is approaches to c is equals cosine of c. Two examples of trigonometric function. First, the limit of sine of x is approaches to pi over 6 is equals to 1 over 2. And the second example is the limit of cosine of x is approaches to pi over 3 is equals to 1 over 2.
In continuity, there are three conditions. First, f of c must be defined. The function must exist at the point of c. 2. The limit of f of x as x approaches c must exist. As x gets closer and closer to c from the both left and the right, the function's value must approach a single finite number and also limit must exist. 3. Limit of f of x is equals to f of c. The limit must be equal at the function value. The value of the function approaches as x gets closer to c must be the same as the actual value of the function.
Continuous over an interval. A function is continuous over an interval if it is continuous at every single point within that interval. A function f of x is continuous at a point c if three things are true. F of c is defined. The function is defined at c. This means f of c exists. There is an actual value for the function at that point. The limit exists. The limit exists at c. As x gets closer and closer to c, the function's value approaches a specific number. The limit is equal. The limit equals the function value. The number the function approaches as x gets too close to c is the same as the actual value of the function at c. If all three of these conditions are met for every point c in the interval, then the function is continuous over an interval. Thank you for watching!